Okay, so today we'll take a look at I guess rejection sampling. All right, sorry, I gotta fix something with my pen here. Okay, and so we'll take a look at rejection sampling. Okay. All right, and first we'll look at the case where we have a uniform proposal distribution. Okay. So again, the idea is we want to generate a sample from some designated PDF, okay? We've already covered inverse transform method, but inverse transform method requires you to find the CDF and invert the CDF, which sometimes can be a hard thing to do, okay? Rejection sampling just requires that you know the PDF, okay? So let's say, let's say our target PDF will be proportional to sine of x, okay? So I've got f of x is proportional to sine of x on the interval 0 to pi. Okay, so if we graph sine of x from 0 to pi, it'll look something like this, right? And the requirement is that the total area needs to be 1. Okay, so so if we say f of x is equal to some constant times sine of x, then we have the integral on 0 to pi of f of x dx has to equal 1. So the integral from 0 to pi of c times sine of x is going to be equal to the integral of sine is negative cosine. So we've got negative c times cosine of x evaluated from 0 to pi. Okay, and this will equal negative 2, I'm sorry, will equal 2 times c. Okay, so if this has to equal 1, then c equals 1/2, right? Okay, so so what I have is f of x is equal to 1/2 sine of x for x in the range 0 to pi. Okay, and what we'll have is a proposal distribution and this will be a uniform distribution on 0 to pi. Okay, and so the idea here is we want to kind of draw an envelope around this thing, and we'll throw darts inside the envelope, and we'll select, we will keep the values corresponding to the darts that land inside the PDF region. Okay, and if we do it that way, then we will generate values according to the PDF. Okay, and so the envelope is corresponds to our proposal distribution. Okay, so this is kind of the distribution of the quote envelope there. All right, is that okay? Got like a frog in my throat or something. Okay, so so if our proposal distribution is uniform on 0 to pi, and we'll call this g of x, what is the equation of g of x? So g of x has to integrate to 1, right? It's a PDF, so the total area has to be 1, so what do we have? The function value is 1 over pi, okay? And this is for 0 less than x less than pi, and then 0 elsewhere. Okay, and so, you know, our picture here, if I draw this, so we have f of x equal to 1/2 sine of x. So what is the tallest value of f of x? What's the max? It looks like this, and what's the height of this? 1/2, right? Okay, and then and if I graph g of x, what do I have? 1 over pi comes along here, okay? So this is kind of the graph of g of x. And f of x is 1/2 sine of x, okay? And so this doesn't create an envelope, right? For an envelope, it needs to enclose it, okay? So g of x by itself is not an envelope. Okay, so what we need to do is we need to multiply g of x by some constant m, okay? G of x by some constant m, okay? So that that the max value of f of x divided by m times g of x will equal 1. Okay. So basically we need to find kind of the greatest difference in ratios, and okay, so what do we have here? For m, what can we use? So if we think of kind of the max difference here, okay, so or in other words, we can choose we want m times g of x to be greater than or equal to f of x for all x, okay? And so for m, we will use pi over 2, okay? So that at this point, okay, so that at a point where f of x divided by g of x is the largest, then the ratio between f of x times m times g of x will equal 1, right? Because f of x, the point where f of x divided by g of x, where that's the maximum, you know, f of x takes on the value equal to 1/2, and g of x takes on the value 1 over pi, okay? So we find this, and this becomes pi over 2, and so that when we divide this, when we include this factor m, this ratio will become 1. So kind of, I should say the max of f of x over g of x is going to be pi over 2. Okay, so we set m equal to that, and now we have our envelope function. So there we have it. Okay, so this is m times g of x, which is basically 1/2 now. All right. Okay, and all right, and so this is how rejection sampling will work. Okay, so we propose x from g of x. Okay, so in this case, we propose a random value of x from uniform 0 to pi. Okay. And then, okay, so let's say let's say we propose x equal to 0.1. Okay, so we're going to propose right here. Okay, then we generate u from uniform 0 to 1. Okay, and so u from 0 to 1 will just be a number, a percentage. Okay, between 0 and 1. And so let's say u is equal to 0.72. Okay, so illustratively, what happened to, did a bunch of my writing just disappear? Okay. Okay, so here we go. So this kind of represents, just imagine we're scaling this so that the bottom is at 0 and the top is at 1. And so we're going to basically throw a dot right here at 70.72 of the way from the bottom to the top. Does that make sense? Okay, so this is 0.72 of the way to the top. Okay, and we will accept the proposed x if u is less than or equal to f of x divided by m times g of x. Okay, so we look at the ratio between f of x divided by m times g of x. Okay, so that ratio is at the very top is at 1, and so on. And if it's inside, if it's below where f of x is, we will accept the proposed x. Okay, otherwise we reject the x. Okay, so in our case, u is 0.72, okay? F of x is going to be sine of 0.1, and m times g of x is pi over 2 times 1 over pi equal to 1/2, okay? So, f of x divided by m times g of x is equal to sine of 0.1, what is that? In radian mode. Okay, I get 0.0998 divided by 1/2, and I get 0.1997. Okay, so u, 0.72, is greater than 0.1997, so we reject the proposed x. Okay, and we will not accept x equal to 0.1 as a value in our sample. Okay, does that make sense? All right, and so how often will we accept the values 0.1? We're going to accept them only according to this ratio, only about 20% of the time, okay? So I will propose all values between 0 and pi with equal probability, okay? And if I accepted all of them, then I would have a uniform distribution between 0 and pi. But that's not what I want. I want a distribution that looks like the top half of the sine curve. And so, in order to adjust for that, we say, okay, values like 0.1, although they are proposed as often as every other value, we are only going to accept those values 20% of the time. Okay? Values in the middle, near like pi over 2. Okay, so values like I don't know, 1.6. Okay, so that's very close. That's 1.6 is a little over pi over 2. Those values get proposed just as often as every other value, and we will accept those values almost 100% of the time. Okay, other values will get accepted less often, and values near the middle will get accepted very often. Okay, and that's how, at the end of the day, we get a sample that looks like our target distribution. Okay, so we will not accept x equal to 0.1 as a value in our sample. Okay, so kind of the big idea is the uniform distribution will propose values like 0.1 with the same frequency or the same probability as all other values in the interval, and in the interval 0 to pi. Okay, but we will only accept 0.1 about 20% of the time. Meanwhile, values near pi over 2, around 1.57, will be proposed, and will be accepted nearly every single time it is proposed. Okay, and so overall, we get something that will look like our target distribution. Okay, and I'm just going to code this up very, very quickly because it's very simple. That's right. A script. Okay, so let's say x, these will be our proposed values, will be our unif. Let's ask for 100,000 of these things on the interval 0 to pi. Let me just make this a little bit bigger. Okay, so if I make a histogram of the proposed values, okay, we see all the values between 0 and pi showing up with kind of equal probability, right? What we have is so f is going to be a function of x, and it returns sine of x, okay? And then g is going to be a function of x, and it returns 1 over pi, okay? And then our acceptance is going to be calculated as, I need u. U is going to be our unif on the interval 0 to 1, and I need 100,000 of these things. And the acceptance is going to be, is u less than the quantity f of x divided by, I'm losing track of these parentheses, f of x divided by m times g of x. Okay, is that okay? So I'm going to propose a bunch of values. I have my target function f. I have my target function is 0.5 of this, 0.5, right? Okay, that's my target function. Oh, and then I have an m, which is pi over 2. Okay, I mean, a lot of these things cancel out, but I'm just including them all for formality here. Okay, so we have our target PDF, 0.5 times sine of x. We have our proposal PDF, g of x, which is 1 over pi. We have the kind of the ratio m, so that the proposal will form an envelope. And then we generate a bunch of random uniform values, okay? And then we will accept if u is less than f of x divided by m times g of x. All right. So far, so good? Okay, what kind of values? Oh, I have to call proposed. Call the function proposed. Okay, sorry. Okay. So acceptance will be a logical vector, right? Yes, question?
Is acceptance less than or equal to?
Oh, yeah, I mean, I guess it probably makes minimal difference, but yeah, okay. So acceptance will be this, okay? Acceptance is a logical vector, and so I can now subset, and we'll say our sample is going to be our proposed values, but we're only going to subset those that were accepted. Is that good? All right, and let's go ahead and make a histogram of our sample then. And what do you know? That looks like the sine function, okay? Because a bunch of the other values, they got thrown away. All right, so I can do plot density samp. That'll look a lot like what we're going for. Okay. So we're proposing values here on the uniform, and then we calculate this kind of acceptance ratio, and then we only keep the proposed values where the random uniform is less than the acceptance ratio. Is that okay? Let's see. Can I copy and paste this here? How do I, how many fonts do I have? All right, let's do this. Okay, so that'll do it, okay? I guess I'll include the histogram. Let's do let's copy this. Great. Yeah, that's good. Okay. So that's rejection sampling in a nutshell. Okay, are there any questions on this? Okay. Okay, so rejection sampling can so this was the uniform case where we had a uniform proposal, and it can the same concept can be expanded to beyond the uniform proposal. Okay, so we'll have rejection sampling kind of okay. General case, okay, so not necessarily a uniform proposal. Okay, so for example, we might have a PDF that extends to infinity. Okay, and if that's the case, you can't do uniform proposals, right? Because there's no uniform distribution that will propose values between negative infinity and positive infinity with equal probability. Okay. Because that means you're just as likely to propose values like 10 to 100 million as you are proposing values of 2 or 3. You can't generate random values on the interval, on an infinite interval, okay? With equal likelihood. So, if your target PDF extends to infinity, you cannot use a uniform proposal. Okay, because then, g of x would be equal to 1 over infinity or something. Just won't work. Okay, so it's basically the same idea here. Okay, target PDF. Oops. We have target PDF f of x. And we have a proposal PDF g of x. Okay, and the only requirement is that the support of g of x has to fully contain the support of f of x. Okay, or f of x, the support of f of x has to be fully inside the support of g of x. Okay. Okay, so then find m so that basically m times g of x is greater than or equal to f of x for all x, and that's basically m is going to equal the max value of f of x divided by g of x. Okay, and then the process will be propose a random x drawn from g of x, draw u from uniform 0, 1, and then accept the proposed x if u is less than or equal to f of x over n times g of x. Okay, reject otherwise. So it's the same process. The only thing that's different is that the proposal PDF g of x does not necessarily have to be uniform. Okay, so here's an example. So let's say our target PDF is the positive half of the normal distribution. Okay. So basically, the PDF of the normal looks like this and has f of x equal to 1 over root 2 pi e to the negative x squared over 2. Okay? So PDF of the, we might call this the folded normal. It will, what will it have to be? Okay, because it has to integrate to 1. So for the folded normal, it's the exact same thing except it's just 2 times this, right? So f of x is equal to 2 times 1 over root 2 pi e to the negative x squared over 2. And now we just say for x between 0 and positive infinity. Yeah? Okay, because the whole thing still has to integrate to 1. Okay. We'll say let's use the exponential distribution with lambda equal to 1 as our proposal. So g of x will equal lambda e to the negative lambda x. So this just becomes e to the negative x. And we know how to sample from this using inverse CDF. Why did that just happen? What just happened here? Oh, that's frustrating. Okay. All right, well, I'm gonna have to look up. Does that ever happen to you guys using OneNote? Stuff just disappears while you're writing it out? I don't know. Okay, I'll have to look that up. Okay, so we know how to sample values from g of x, okay, using inverse CDF. So it's not a problem. Okay, so we've got g of x there, and this, you know, this looks like this. Okay, so we need to find the maximum value of f of x over g of x to get our m, okay? So we must find max of f of x divided by g of x, okay, to get m. Because we're going to use that so that it fits, right? Because right now, if I plot this, we've got this thing, and then I probably have this thing, and we need to find kind of this spot. If this is f of x up here and g of x down here, we need to find it so that g of x will form an envelope. Is always bigger than f of x. All right. So this is a little bit of work here, but it's going to be the max value of 2 over 1 over root 2 pi times e to the negative x squared over 2. That's the f of x on top. And the g of x is going to be e to the negative x. Okay. And so the max here, if I include this, so you got 2 over 1 over root 2 pi. These combine, so I have e to the negative x squared over 2 plus x, or, you know what, let me factor this out. Factor out the negative, okay? I'm going to have x squared over 2 minus x, okay? So that's what I have here. And so what I have is the x that maximizes this function will be the x that minimizes the kind of the parabola x squared over 2 minus x, yeah? Because if I minimize this thing, then this thing will be e to the smallest negative thing, and that'll be the maximum value of this function here. Okay, so we have x equal to 1. Okay, that's going to be the smallest value that we can get here. Right? I mean, well, I'll back that up. Okay. X squared minus x. So if we do d dx of x squared minus x, we have x squared over 2 minus x. We'll have x minus 1. Okay. So critical value at x equal to 1, and that'll be the one that minimizes. Okay, so m is going to be equal to 2 times 1 over root 2 pi e to the negative 1/2 minus 1, and this we get something around 1.32. So that's going to be my m. Okay, and then now it's just a matter of using this to do rejection sampling. Okay, so let me kind of demonstrate that. Okay, so U1 will be R unif 10 to the, well, here, we'll just do random exponential. I was going to do, so our proposed will come from random exponential. And we'll do 10 to the 5th, rate equals 1, okay? Our f of x is 1 divided by square root of 2 times pi e to the negative x squared over 2. That's our f. Our g of x, oh, and I'm sorry, it's 2 over square root 2 pi. And our g of x is e raised, exp raised to the negative x, okay? Our m is around 1.32. This is what we calculated. And so we'll go ahead and just do this. And let's, oh, that doesn't look quite right. E to the negative x squared. G of x is e to the negative x. Random exponential. Did I mess something up? Oh, square root of 2 pi times. Okay, that's correct. All right, so if I plot this, sure enough, this looks like half of the normal distribution. Okay, I was just missing a multiplication sign here. Okay.